All right, folks, let's go ahead and get started then. I think we're going to be able to wrap everything up today that we need to wrap up. So this should be pretty much the last lecture class meeting for the semester, unless something pops up where I just don't get to be where I need to be, but I think we're going to get there. All right, so I want to recap here, and I've just written out a few notes here to recap pretty much what we talked about in the video for last night. So I just want to redefine what a hybrid orbital is. And it's basically a method or a model to show how covalent bonding can be consistent with molecular geometry as governed by VSEPR. And we looked at an example of this in the video with CH4. So if you notice that if I write CH4 out as a Lewis structure like I have here, you'll see that we can do it, but we show 90-degree bond angles. But we know we can do better than that, because if we apply VSEPR, we can let those bond angles actually stretch out by putting this thing into a tetrahedral geometry. So we can get these bond angles of 109.5 degrees. The problem is this just doesn't really jive with or agree with what we end up predicting if we just look at regular old atomic orbitals. All right, so this is the problem that we run into. So rather than using atomic orbitals like regular S and P orbitals, what we need to do is to take S and P orbitals and hybridize them. All right. So essentially what I have here is a situation where I can focus on the carbon atom. So here's an unhybridized carbon atom. And if we look at it, we have two 2s electrons, and then at a slightly higher energy, we have our two p electrons, each one inhabiting its own p orbital. So what I want to do is I want to make hybrids out of these. So I'm going to make something that looks a little bit like an s orbital and a little bit like a p orbital. And by doing this, I'm going to bring the energy of the s orbital up a little bit and the energies of the p orbitals down a little bit. So now I end up with this thing that I have on the right, which is the hybridized carbon. So now notice I have my four orbitals that I originally had, but now they all lie at the same energy. And I can distribute the electrons equally amongst them. All right. So now I've got a situation where each hydrogen can come in, donating its electron into one of those hybrid orbitals to form a new covalent bond. And that's what I'm essentially showing there. Now, what does a hybrid orbital actually look like? Well, one of these hybrids between an S and a P actually looks something like what I've drawn right here. Okay, so it has a little bit of S character, as you can see with this little bulb of density to the left of the carbon. And then you see what sort of residual of the P lobe there coming out to actually interact with the hydrogen atom that's brought in. So since I need to make four of those because I'm making four bonds, what I can now do is arrange them in three-dimensional space as directed and required by VSEPR to get the 109.5 degree bond angle. So that's the nice thing about the hybrid orbitals, is they all lie at the same energy, so I can arrange them in any way in three-dimensional space that I need to satisfy the requirements of VSEPR. So this is what the full-on hybridized CH4 molecule would look like. Okay, so you can see it's a combination of these hybrid orbitals, the four of them that I made, arranged in three-dimensional space as a tetrahedron. Okay, so that's pretty much summarizing what we did in the video last night. So that's kind of why I threw it out there like that. Just a real quick summary. So now I want to start with the new material, which is sort of building out on this. So what I want to look at are a few other examples to derive some different kinds of hybrids. And then we're going to show you the easy way of looking at this. Okay, there's actually a nice easy way of identifying the hybridization on any atom in a given molecule. And I'm going to show you that. But let's look at these other cases first. So these are sort of the classic cases. A C2H4, okay, that's called ethylene, by the way. It's an organic molecule, a hydrocarbon. And if I were to draw a Lewis structure for ethylene, it would look like this. You guys could verify it. All right, so what I want to look at is each carbon. I want to focus on the hybridization of each carbon. Now you'll notice that the carbons are symmetrical, right? So they look the same. So if I focus on any one of the carbons, what I can show here is that it's going to be of a trigonal planar geometry, right? It's an AX3 situation. So that means the bond angles have to equal to what, 120 degrees. All right, so that's going to be true for both of those carbons. So what I need to do is to come up with hybrid orbitals that are going to allow for this trigonal planar geometry that I know that I need to get. Okay, so let's see how we're going to do this. Now, the first thing I always do is I go back to those energy diagrams that I showed you before, where we show the hybridized and the unhybridized atoms. So my carbon atom here, unhybridized, is my 2s with my 3 2p's. Okay, so the thing I want to think about when I go to the hybridized situation, which is what I have here on the right, is how many bonds do I have to make out from that carbon to other things? So it looks like I need to make 3 bonds. I've got a carbon bonded to a carbon, but the carbon's also bonded to 2 hydrogens. Okay, so that defines for me how many hybrid orbitals I got to make. I need 3. I'm going to make 3 bonds to the carbon, so I need 3 hybrid orbitals. So what am I going to hybridize? Well, I'm going to hybridize one of these s orbitals and then 2 of these p orbitals to get me the 3 hybrid orbitals I need. So what I'm going to end up with is a situation like this, where here are my 3 hybrid orbitals, but then what I've got over here at higher energy is the unhybridized p orbital that I did not use. Okay, so this set of orbitals here that I did use to make the hybrids, we're going to call those sp2s, a set of sp2 orbitals. Now, why do I call it that? Well, it's because I had to hybridize an s orbital and 2 p orbitals. That's where that terminology comes from. If you look at my prior example with the methane, we needed 4 bonds. So I needed to hybridize a 2s and all of the 2 p's. So that's why we called it an sp3. All right. So how would I actually draw this thing? Well, again, focusing on one carbon, and if we do one carbon, we can come back and see what happens with the other carbon. I'm going to need my 3 hybrid orbitals. Okay, so I'm going to sort of draw them here. I'm going to sort of show this in a trigonal planar geometry. So first of all, I know I'm going to have to come out with a hybrid from my carbon, and this is going to be my carbon on the right, the one we were focusing on, and then we'll come back and fill in the one on the left. Okay, and then I know I have to hybridize out to form bonds with the other hydrogens. So I'm going to sort of show this bond going out at 120 degree bond angles. Then I have another one that I have to make here that's kind of coming out again like this, and I'll sort of slash this in to show that it's coming sort of out of the plane. And then I'm going to put my hydrogens in here. Okay. And then I've got my other carbon over here. So let's go ahead and fill that guy in while we're at it. So here's the carbon on the left. So we're going to do the same thing because it's totally symmetrical, right? So we'll show those hybrids overlapping like that. And then I've got one coming out like this. Sorry. We'll slash that in because that's coming out of the plane. And we have another one going back into the plane like this. Okay, so what you can see here is I've satisfied those 120 degree bond angles all the way around on both sides. Okay, but remember, each one of those carbons still has an unhybridized p orbital associated with it. Okay, so if we're kind of looking in the XY plane here, okay, I've still got essentially a PZ orbital, let's say, that I haven't hybridized. So what I'm going to do is I'm going to draw that PZ orbital coming up and down like this. I'll just label it as a P so you know that it's p orbital and not a hybrid orbital. And the same is true on the other carbon. There's a p orbital up and down. Okay, now here's what happens. We actually end up getting 2 kinds of bonding here. We get the direct orbital overlap bonding from carbon to carbon that I show you here. Okay, this one right here. But it turns out I also get a different kind of orbital overlap, which is sort of a side-to-side orbital overlap, which I'm going to sort of show this way, between those 2 unhybridized p orbitals. All right, and we have a name for this. If we have direct orbital overlap, this is going to be called a sigma bond. If I have indirect or side-to-side orbital overlap, like between the 2 unhybridized p orbitals, that's called a pi bond. Okay, so just defining that. A sigma bond is direct or end-on orbital overlap. And a pi bond, we're going to define as indirect or side-on orbital overlap. Now, if we go back to the Lewis structure here of this thing, let's just back up for just a second. Look what I've got between the two carbons. I got a double bond there. See the double bond? Now, we have a new definition now for a double bond. A double bond, as it turns out, is going to be a combination of a sigma bond and a pi bond. So I have to have both of those there to get a double bond. So what does that tell me now about a single bond like I have between the carbon and the hydrogen? Well, that involves direct orbital overlap. So that must be indicative of a single bond. Okay, so let's go ahead and put that down as well. A single bond, like we have between the carbons and the hydrogens, is indicative of a pi bond, or sorry, a sigma bond, direct orbital overlap. But if I have a double bond, like I do between the two carbons, what does that signify? Well, it signifies a sigma bond plus a pi bond. Okay, so anytime I see a double bond, I know that I've got both a sigma bond and a pi bond happening pretty much simultaneously. Everybody okay with that? All right, so let's take this one step further now. So I could go all the way to a triple bond if I wanted to. So the other example of this is going to be C2H2, which is called ethine. And if I do the Lewis structure of ethine, it looks like this. It's a triple bond between two carbons, and then you have a hydrogen coming off each carbon like this. Okay, so you can look at this thing and you can tell that I've got a linear structure with a bond angle of 180 degrees. All right, so now let's go back to our energy level diagram real quick and see what we have to do, just focusing on a given carbon. So I'll focus on the carbon on the right again here. So starting with that carbon, I know I have a 2s and I have available to me a set of 2p's. Now, to make my hybrids, how many bonds do I have to make out from each one of those carbons? Well, I look and I see that I have a carbon bonded to a carbon, and the carbon also bonds to the hydrogen. That means I got 2 bonds out from the carbon. So I have 2 bonds. That tells me how many hybrids I got to make. I need 2 hybrid orbitals. So what that means is I'm going to hybridize a 2s and a 2p. So now what I've got is a situation where I have 2 hybrid orbitals, and then I've got 2 unhybridized p orbitals here. And then I'm going to call this set of orbitals an sp. Why? Because I hybridized an s orbital and a single p orbital. Okay, and I'm leaving behind 2 unhybridized p orbitals. Okay, it's because I only need to make 2 bonds to each carbon. So now it gets kind of funny to try to draw this, but let's see if we can do it. I've got a carbon and a carbon here. So let's just focus on the carbon on the right here and know that everything to the left is going to be symmetrical. All right, so I know I got to make a bond into that carbon. And I know I also need to make a bond out to the hydrogen to satisfy that 180 degree bond angle requirement. Okay, but I've also, on that carbon on the right, I've got 2 unhybridized p orbitals I have to account for. So I'm just going to kind of put them up here like bunny ears. It's kind of hard to draw. But basically, we've got our 2 p orbitals that we didn't hybridize here. Now, the same thing's going to be true to the carbon on the left. I'm going to hybridize in to form the bond of the carbon on the right. I also have to hybridize out to form the hybrid orbital to the hydrogen that I need there. But remember, I also have 2 unhybridized p orbitals on that carbon as well. So we'll put our bunny ears in here. I got a p and a p and a p and a p. So take a look at this and see what kind of bonding we've got. If I focus on the carbon, right, I see that I have a sigma bond here. I got a sigma bond here. I got a sigma bond here. But I also got some pi bonds, don't I? I got the direct or indirect orbital overlap happening basically between these two guys here. Showing both of them here. So if you look at what I've actually got here, I've got a pi bond and another pi bond plus a sigma bond. Okay, so a triple bond now is going to consist of 1 sigma plus 2 pi bonds. Okay, so again, you've got your end-to-end orbital overlap here with the sigma bond, but then you've got the indirect orbital overlap times 2 happening with the 2 unhybridized p orbitals on each carbon. Okay, so a triple bond is 1 sigma and 2 pi bonds. All right, so you can kind of see how this is going to go. Now that's sort of showing you the derivation side of this thing, but I'm telling you there's an easier way to do this. Okay, so this is really what we can fall back on. So let me show you, for example, let's do CH2O and show you the quick and dirty way of doing this. All right, so if I draw a Lewis structure for this thing, let's see, we're going to get 4 electrons from carbon, we'll get 2 electrons from hydrogen, 6 electrons from oxygen, 6, 7, 8, 9, 10, 11, 12. So I've got a total of 12 electrons to work with. Carbon goes in the middle. Okay, we'll put a hydrogen on either side of it, and we'll put an oxygen up here. Make our bonds. 1, 2, 3, 4, 5, 6, go to the oxygen. 7, 8, 9, 10, 11, 12. So we see what we got to do here. We got to make a double bond from the oxygen down to the carbon, right, to get the carbon an octet. So we'll have something that looks like this. And if I get the geometry right, we see this is an AX3, which is going to be a trigonal planar geometry. All right, so I look at this, and now I can apply hybridization to this. Now, the easiest way to do it is to just kind of look at how many bonds I got to make. Okay, so let's do the carbon first. So if I look at the carbon, I ask myself, how many bonds do I have to make? I got to make a total of 3. So how many hybrid orbitals do I need? I need 3. So what is that going to be when I hybridize the carbon? That's an sp2, isn't it? Right, because I needed to hybridize an s orbital plus 2 p orbitals to make those 3 bonds. Now the hydrogens, they don't hybridize, right? We don't need to worry about assigning hybridization to them. But I do need to assign hybridization to the oxygen. So here's the rule with that. Remember that I also need to house these electrons here on the oxygen. All right, so in a sense, I'm going to treat this like 3 bonds. So when I do actually have electron pairs on the outer atom, can I actually assign those to hybrids? Yes, I can, even though I'm not actually bonding anything. So I'm going to do that. I'm going to assign them hybrids, act like they're bonds. So how many bonds am I making out from the oxygen if I count the electron pairs as bonds? Well, it's still 3. So as a result, I know that the oxygen is also going to be sp2 hybridized. All right. Now, one other thing I want to show you, kind of moving along in the same direction, is what do we do with expanded octets? We haven't seen that yet. Well, let's look at an example. Now, the nice thing about expanded octets is that we can actually hybridize d orbitals as well. So if we can do S's and P's, we can also do D's. And remember that expanded octets come into play when we put electrons into d orbitals. All right, so let's look at something like an XeF4, xenon tetrafluoride. Okay, I think we did the Lewis structure for this one already. And when we did it, what we ended up with is something that looks like this. Actually, I'm going to show it as a square, which is a square planar geometry. So I'm going to put the electron pairs here on the xenon. And then what we're going to end up with is a situation where I've got showing it in via CPR. And we might as well go ahead and put our electron pairs around the fluorine so we know they're there. And again, you guys can verify this structure from the Lewis structure, but we did this one earlier in, I think, a couple lectures back. All right, so here's what we end up with. You can see that you kind of got a square planar geometry out of this thing. It's octahedral parent, okay? So it's an AX6, but it's really got the two electron pairs on it that we kind of have off on the axial ends, and we can see we get a square planar geometry. So we know that we need 90-degree bond angles here. All right, so what about actually putting hybridization on everything? Well, let's do the fluorines first. They're all the same, but those are kind of easy to do because how many bonds are we making out to the fluorines if we're actually counting the electron pairs as bonds? It looks like 4. So if you have 4, that means the fluorine has to be sp3 hybridized. Okay, so we've got to have our 4 hybrid orbitals to stick all those electrons into. But what about the xenon? Let's look at the xenon. How many bonds do we have coming out from the xenon if we count the electron pairs as bonds? It looks like 6. Okay, so how would I hybridize the xenon? Well, I can use S's and P's. So the best I can do there is an sp3. So that gives me 4 bonds, but I need 2 more, okay, to accommodate, let's say, those electron pairs that are going axial there. So where would I go after the D's? Or sorry, after the P's? Well, the next set of orbitals I have to play with are those low-lying D orbitals that we talked about that we can use. So I can hybridize as many of them as I need to make the bonds. So I could do an sp3d2 and now count them all up. You've got 1, 2, 3, 4, 5, 6 hybrid orbitals to account for all the electron pairs bonding and non-bonding around the xenon, okay? So you can see how I don't really have to derive those hybrid orbitals like I did in those cases. I can really just kind of look at how many bonds I need to make, how many electron pairs do I have to accommodate, and then I can define my hybridization simply by doing that. All right, we'll do one more example before we head off into Chem 101. Let's just do carbon dioxide. That's just a simple one that we kind of already know how to do. So carbon dioxide, we'll just go right to the Lewis structure here. Looks like that. Okay, we know it's a linear geometry, 180-degree bond angles. So let's do the hybridization on each of these guys. All right, so there's carbon. How many bonds are going out to the carbon? Looks like 2. So how many hybrid orbitals do I need to make if I'm going to have 2 bonds? I need 2 hybrid orbitals. Carbon hybridizes through S and P's. So that means I've got an sp hybrid on the carbon. What about each oxygen? Well, again, count up the bonds and the electron pairs. I got 1 bond and 2 electron pairs. So that looks like I need 3 hybrid orbitals, okay? So that would be an sp2 hybrid. All right, that would be the same for both oxygens because they're symmetrical. Okay, so you kind of sort of see how we go about doing this. Any questions in general, guys? All right, let's go practice a little bit. Real short practice for you guys today. And by the way, while you guys are working on that, I just wanted to let you know that even though we won't need to meet next week, I'm going to go ahead and keep office hours as I normally do, so you guys can access me if you need to. And the other thing I'm going to do is I'm going to send out an email and post on D2L for you specifics about the final exams. We already talked about when it's going to be, what the format's going to look like, but I just want to reiterate all of those things to you. I think somebody also asked in the chat last time whether or not you would be required to be on Zoom for the final. I don't require you to be on Zoom for the final. I'm not going to put a camera on you or anything like a lot of people do. I'm going to be on Zoom. So if you guys need to log in and ask a question or something like that, you can contact me. But I'm going to be tracking the progress of the final on Chem 101. So I'll be on both Chem 101 and Zoom if you need me. And I'll reiterate all of this in my email out to you guys so you know what's going on. And I'll also remind you about the homework being due, I think, Sunday by midnight. And then I think your exam's the next day. So staying on top of that homework, using that as a chance to actually keep practicing for the final. And that's probably the best way to practice for the final, is to keep working away on the homework. But I will reiterate all of that in writing for you guys, so you'll know exactly what you're dealing with. Yeah, it looks like you guys are getting this. All right, guys, any further questions about this? I see I've got a few of you still here. Any further questions, comments, concerns? All right, folks, I'll see you at exam time. Like I said, I'll be available if you need me.
Thank you.
Sure thing. Have a good one.